Okay, so this is going to be the more advanced KiCAD tutorial. The plan today with this is for me to go over how to create your own symbol and how to create your own footprint. So generally, as you saw like in the basic KiCAD tutorial at the beginning, when you click this op-amp here, you get a bunch of symbols that are already included in KiCAD and also ones that have been made by other Solar members. But there are times whenever you want to make a footprint or a symbol and you want to use a certain component, but it just doesn't have it there, which it's not an issue. We just have to make our own one. But one thing I want to note, because I never actually explained this before to people, but with a lot of ICs or like integrated circuits components and microcontrollers and stuff like that, there is a general like standard for them. Let me see if I can find them. A general standard, so that way you don't actually have to create it all. It just lets you know that it is a certain size. Oh wait, this is not going to be the symbol. This is going to be footprint. But let's say there's a component that you want to make that it's not there. So the way to do this is you want to go, you could go from this page as well, but if you go here, there's a symbol editor and there's a footprint editor. We're going to start with this footprint editor because that's what we want, or the symbol editor, since that's what we want to start with first. That way we can put it on the schematic. So I made this one already, but I'm just going to go over how to do it with the same one. And so this, what you're seeing here is the integrated circuit that it's called the AS8510. They call it like a data acquisition device for battery sensors, but what it does is we're using it to measure the current across a shunt resistor to see, and the shunt resistor is a resistor that's you're trying to measure the voltage across of, so that way you know the resistance of it and you know the voltage of it, so you can use Ohm's law to find the current of it. So this is the IC or integrated circuit that we're using for the BPS is using in order to measure the current, so that way it can monitor the current to see whether there's an overcurrent or undercurrent. So we want to see whenever you're starting to make footprints and symbols, the data sheet is going to be your best friend. So you're going to want to go to the data sheet, especially when you're designing your own circuit too. There's a lot of times, and you're not given a schematic. If you scroll up to some point there's often a diagram that says common applications and how to connect everything here. So it's telling you once a bypass capacitor between VDD, which is power, VSS, which is ground, and it tells you the general layout. For some boards, you won't have to worry about that. For others, when you have to start completely from scratch, you do have to worry about doing this, because this one allows it to optimize its performance. But the data sheet's going to be your best friend with a lot of this. So if you come here, it tells you pin assignments. The pin assignments is what you want to focus on whenever you're creating this symbol, because what you're doing, and let me go back to this schematic page here, and let's look at a common microcontroller that we use for the BP or the other teams use. I forgot the exact number of it, but I guess it doesn't really matter for the point that I'm trying to make here. So this is a microcontroller, and notice how there's looks like 32 different pins, and this is what a symbol and this is what you're trying to make, is that you're trying to say, okay, so pin 4 is connected, and then NRST is like the reset pin. So you're connecting. So now whenever you're laying out the schematic and you're connecting something to this pin here, you know you're connecting it to the reset pin. So, and notice how it's not necessarily in numerical order. Like it doesn't go, you don't have to do 1, 2, 3, 4, 5 with the symbol. And the symbol isn't actually what's going to be placed on the board. So here it's just nice to make it easy to work with, easy to see. A lot of time power is facing the top, ground is facing the bottom. Here you have all the pin A pins from 0 to 15, and then the PB pins and the PF pins. So that's kind of the goal that you're trying to do, is make something like this that's easy to work with, easy to connect things to, so that way you can, when you're designing your schematic and your circuit, you're able to connect it and do it. But since for the AS8510, um, the libraries that came with KiCAD or KiCAD didn't include that already, so that means we have to make it ourselves. So if you go to here, file, you don't have to, for this sake, you don't need to create a new library. But if you do, I'll just go through the process of it. Notice how there's like a .lib file here, and when you go to the UTSVT KiCAD libraries, there's a .lib file. So that's going to save and store all the symbols that you make. But here, let's just call it workshop.lib, because that's what we're going to do. We're going to save it here. We could just call it global, so that way other projects can use it as well. And then you want to create a new symbol. I think you could click on this button here. You want to choose the symbol library, and we just made a workshop video, so we'll just use that. And now we want to call the symbol name. Symbol name is what you generally want to use the name of the part that you're doing. So here this one's the 8510, AS8510. So that's what I'm going to type here for the symbol name. You don't have to, and other than that, you could just kind of keep all the other default settings. Now here you have U. U means that it's going to be a microcontroller, because when you look, an easy way to remember that is that U is, it's supposed to really be the micro sign, which is almost like a U with the tail on it. So you have the AS8510 here. So now you have the reference designator and also its name. Now you want to create your symbol. And so you could start with either one. Generally, I like to start with the pin assignments, because I don't know how big the rectangle is going to be. That meaning, let me replace that STM here. So I don't know how big this rectangle is going to be. So I like to start sometimes by using just the pins first, so that way I don't have to remake the rectangle later on. So let's go back to the data sheet. Sometimes it helps to have like the two windows open side by side. That way you could just go back and you don't have to constantly go back and forth. Okay, so for the sake of this tutorial and whenever you're making a symbol, you technically don't actually have to know what all of these actually mean, but if you're designing the circuit that has it, it's good to have an understanding of what that does mean. Okay, so we're going to start by placing pin 1. We're going to do pin name. This one's RSHH, which is the, if you look here, it's the positive side of the current channel, so it's going to be placed in the positive end of the shunt resistor. And then pin number, I want pin number 1 to do here. A lot of times for pin or electrical type, some data sheets will actually specify what the pin type is. If it doesn't specify pin type, you want to make your best like guess almost of what it would need or what it would be depending on what you know the pin does. So here it says analog input, so I'm going to keep it input, and then these you could just keep the other settings the same. And so you could do it like here and here. You just place it. You could drag and move it. Same exact shortcuts and tricks as when you're laying out your schematic. So let's do RSHL, that's pin 2. That's also an analog input. So we could just put that right below it here. And then ref here, pin number 3, it says it's an analog output, so I want to change it to an output here. And then here. And then we want to do DCM for that also says it's analog output, so we'll do that here. And right now I'm kind of just arbitrarily placing the pins in there, and then I'll be a little more selective whenever once I make the rectangle and decide where everything wants to be. Pin 5 is going to be A, B, D, C. That's 5. It's a power, or it says supply pad here for pin type, and notice how if you go to the description, it's the analog power supply. So it's going to be a powered input. And so we want to do that. And then do ADSS, and that's going to be 6. And that's powered input as well. Then you could do 7. And then so on. Probably would have been smarter to do something that has less pins on it so it wouldn't take as long. But I'm gonna quickly do this right now. Does anyone have any questions so far on what I'm doing or if something doesn't make sense? Okay. At any point, you guys are free to stop me and interrupt me if you do have a question about something that I'm doing or something doesn't make any sense. Or you're wondering how I'm doing something. So that was just rotating it because you want the pins, like these little circles, to be facing outwards, not inwards. Generally speaking, I don't want to say anything with 100% like different, like with certainty, because I'm sure there's exceptions to a lot of this. But generally, you want all the pins to be facing outward because you want to make sure you're connecting it to something external to the symbol, not internal to the symbol. And then a few more. And this does take practice and time. So if something doesn't make sense, you're always free to ask any questions about anything that I'm doing. Okay, so I'm going to finish laying out all the pins here. And 19. So if it says IO, then it's going to be bidirectional because it's going to be input and output. And then SDI should be input. And then before I forget to tell you guys, sometimes for whatever reason, there's pins that don't actually need to be connected to something. So on this microcontroller or on this IC, all of these do need to be connected to something. But if you know for sure and it says not connected, you could just not connect it from the very beginning, so you can't connect anything to it. But in this one, there isn't any pin like that. So you lay it out. And so now you have all the pins that you want. And so after that, I would want to kind of move things around. I like having all the power space up and the ground space down. So here, I would move this space up here. And then the other VDD, I'll make it place up as well. And then I'll have VDD facing downwards here. And then I'm gonna have to move some things around here. And then after that, and let me move this. After that, I like to kind of group so I like to have the power pins face up and then the ground pins face down. But after that, what I like to do is to kind of group the pins based on what its function might be. So RSHH and RSHL, since they're both connected to the current channel, it makes sense to group these two together. The reference reference pin, and then the VCM pin might not have a clear grouping, so that's okay. You could place them where there's room. ETR and ETS are both connected to they're both related to like the voltage channel single-ended input, so it makes sense for these to be together. And then it also makes sense for VBAT and VIN to be together. On the other side, so SDO, SC, and then SCLK, which stands for the clock. And then the CS pins make sense because they're all related to SPI, as you can see in the data sheet. If you don't know what SPI is, you don't worry about it. You'll learn about it in 319K, which I think a lot of people take towards the beginning of when they're a double major. But what SPI is, it stands for Serial Peripheral Interface, and it's a communication protocol that allows this integrated circuit to communicate with other integrated circuits and ICs. So you want to keep those together. So it looks like clock is kind of like its own entity, so I'm just going to put it on its own. And then that might actually go well with the MEN pin, since they're connected for similar applications like high side and high side. And then the clock and the notice how SDI here is also related to SPI, and so it's a good place to kind of mix up the order of it, even though it will be hard from a numerical standpoint. It's easier to see it in the circuit, and then we could just have like the interrupt and the clock pin be here, and then these be here, and then we could just put this here. So it's good, also good practice to kind of like align things and try to make things centered and straight, just because it just makes it easier for everyone if things are neater and easier to look at. So what I would like to do is kind of like count the dots, even though that's kind of time consuming, just to make sure this is the same distance away from this. That one's 11 and then 1. Okay, so this one's 10. So I can move that over 1. So then once you have all the pins numbered, you can lay out the rectangle. I think I said this earlier, but you could lay out the rectangle first too. It's actually, I don't, you could lay out the rectangle first. You could do it in either order. I just like to do this because so that way I only have to lay out the rectangle once and I don't have to worry about it again. Okay, so also notice down the STM here, it's filled in yellow. It kind of looks nice that way. So what you could do is right click on the rectangle you just made, or click E, or hover over and click E. Okay, not exactly sure. Okay, so it seems that I'm gonna save this real quick. It's not really responsive to my keyboard right now, so I'm sorry that it's acting weird right now. Let me see if that helps. Okay, so now you have here, you could hover over it and click E. So notice that it says fill with body background color. You can select that, and now it's yellow. And it looks like this. And so that's how you create your own symbol. You can move these closer as well. and center if you want to. And so now you have your symbol. You can save it, and then after that, it's good to, you could technically end it here, but it's generally good practice to also edit like the symbol properties here. So this references you there. So if you have a footprint, which we're gonna make the footprint for this, when later on when you go, you could come back to the symbol editor and we could do this together. You could come and edit this footprint so you can add it so that way you don't have to manually add the footprint every single time since this one only has one footprint. You could write a description, so I could just write what the data sheet says here. Data acquisition device here. Keywords, you don't have to put that there, and then they include a link to the data sheet so other people can refer to it as well. And then press OK. And so now you can create your own symbol like this. So you close it, and you come back here to delete this. And so let's say we want to add it back now. Okay, so if you go to, notice how workshop is now a library, symbol library, and now you have here, which is the symbol that you just made. And so that's how you make a symbol for symbols that aren't provided already in the date or in the libraries that are given to you. So now we need to go and make its kind of real life equivalent, its footprint, so that way we're able to lay it out on the PCB. So the way you do that is you want to go here and you want to click here, which it says footprint editor, and you want to open that. So right now we want to create a new footprint. You can also, there's also a footprint wizard that you're able to create certain kinds of footprints, such as like, I think one of them is like a capacitive touch sensor and stuff like that. But generally we'll do new footprint here. This one's the AS8510, so we'll stick with that here. Okay, so now you're starting on a blank slate. Now we have to go back to the data sheet again. And now we want to find out its dimensions. Now this part is a lot more crucial than, so the schematic part, the importance when you're creating a symbol, you want to pay attention that you're assigning the right pin numbers to the right pins. Because if you mix it up and then lay out the trace that way, then you're connecting it to the wrong pin. And so make sure you double check that whenever you're working on that. For the footprint, what is important about creating the footprint and what you want to pay attention to is making sure you have the dimensions correct. You want to make sure that its size is correct and the size of all its copper pads are correct, because if it's not correct, then you may not be able to fit the component there, or it may be like the footprint that you make might be too big or might be too small for the footprint, or it may not have a correct connection in the right place. So that's something you want to double check and make sure that all the measurements are correct. Okay, so it's usually at the end when you find out its recommended PCB layout. Here on page 45 here, you get a recommended PCB footprint. A lot of times you'll find this. If you can't find it, then you kind of have to estimate it, but generally you will be able to find a recommended PCB footprint. So notice here that it tells you that the distance from this pad to this pad, so these are representing the copper pads that you place the IC on and that you solder the pins onto them. So notice how it tells you that this distance from here to here, it should be 9.02 millimeters. And then here should be 6.31 and so on. So notice that it gives you all the measurements that you need to figure out what it doesn't give you. Notice that it doesn't actually give you the length of this copper pad here. It tells you what A is and it tells you what B is. So this is what I mean whenever you have to do a lot of math involved. So if you want to see the length of this pad here, you have to take A minus B and divide it by 2, since there's 2 of them. So it's 9.02 and then 6.16, you subtract it, divided by 2. So now you know that all these copper pads, its length is 1.43 millimeters. So you're going to have to do that because they give you all the measurements that you need to find out all the ones that you can. But it doesn't give you, a lot of times it doesn't give you more than that. So you're going to have to do the measurements on your own. So that's, or do the calculations on your own. So when you're starting to make it here, I'm going to go back to the footprint editor. Um, Come back to the footprint editor, and it's nice to sometimes have it side by side, at least initially, but you might want to make this screen bigger just because the size is, it's hard to work with if it's too small. So the first thing you want to do is lay out the copper pads. So notice here, this is standing, it just means pad, but notice that this is a through hole component because there's a hole in it. We don't want a hole, we want a surface mount thing. So if you click E, hover over it, or you place it, escape, and press E over it, then notice that you have options here with pad type. You could do surface mount, you could do connector, you could do an PTH, an aperture. For most part, you'll stick to SMD and through hole. Uh, Um, to be honest, I'm not entirely sure what these will be used for, but I'm sure it has a use for it. So now you have this. Notice though that this is circular. We want it to be rectangular. So you have options to change the shape too. You can do oval, rectangular, trapezoidal, rounded rectangle, and custom. We'll stick with the rectangular one here. Also notice this is a square. We want it to be in exact dimensions. So remember the A minus B divided by 2 calculation to get the length of the pad? That's what we want at the moment. And so that's going to be 1.43 millimeters. So for size Y, actually I think we said X. Size X will do 1.43. And then for size Y, we will have to see, it looks like they gave us that value C, so we don't have to calculate it, and it's 0.46 millimeters. You want to also make sure that the units are correct. You could toggle the units between inches and millimeters here. I prefer millimeters, but if you want to do inches, you can do inches as well. So you do 0.46. So this looks a lot more like the recommended PCB footprint layout that they gave us here. Eventually, you can also change the positions as well, and I will point out when that's important now. You could change the offset and the pad to die length. But for the most part, and you can also change like the clearance setting, and you could change the shape. But for the most part, you want to have the pad number, the pad type, shape, position X, position Y, size X, size Y. Those are the most important things that you'll probably be working with. You can also change the orientation, but in this case, you probably don't need to. And generally, we do everything on the front copper layer, assuming it's on the front, because you can always flip it on the back if you want to. So you do here, and you place it. Okay, so if you press C, and then now if you go and click add pad, notice that it copies the exact pad that you made before. So for now, I'm just gonna kind of arbitrarily lay out 20 of these because that's how many we need. The good thing about this software is that notice that each time I want a pad, I don't need to go here. I can just click it, and I can just click, and it makes it a lot easier to work with, and it definitely simplifies having to do everything. So now you have the 20 pads that you're working with. There are cases whenever the pad size might differ, so you might have to change it and do it again. But in this one, all the copper pads are the same exact size. So that's what you want to do. And there's 20 of them because if you remember from the symbol, we made 20 pins. So we want 20 pads. This part here, it just means the squiggly line here just means that this top part or all the measurements are just going to be consistent all the way to the end. Some of them won't actually specify that, but here it says it's all going to be even. So now it's important that we measure everything out and make sure everything's spaced out exactly the way we want to space it out. Okay, so the first thing we can work on is we can actually lay out and make sure the distance between this pad and this pad are the same or are correct. So if you go here, measurement D, from the center of this pad here to the center of the next pad, the distance is 0.65 millimeters. So that's what we're going to work with. Whenever you look and you hover over it and press E, and you get position XY. What position XY is the position of the center of the pad, not like either of the corners or edges, it's the exact center. So for the first one, it doesn't matter what it is, but we want to focus on Y right now because we want to make sure that everything is 0.65, the centers are 0.65 millimeters away from each other. So you have position X. Also, we do want all the position X's to be the same for this row of paths. So generally, if you want to make it easier, you can move it here, and then let's just start off like that. That's where we want it to be, so that way it's easy to remember. So here, okay, so we want X to be the same because we want it to be directly below it. But we want Y to be a little lower. So that was 9.65. As you go down, it's becoming more positive. So that's it's like reverse thing. So 9, and then it's going to be 8.35, I believe. And then if you're going to the right, though, so positive Y is in the bottom direction and positive X is in the right direction. So it's a little opposite of your typical XY planes. And if you want to double check that the center of 1 is actually center away from 2, I'm going to change my grid size to 0.1. You can use this inspect measure distance tool. Go to the center of this. I'm going to have to make it a little more behind here. Go to the center of 1 here, and then to the center of the next one. Notice that it's exactly 0.65 millimeters away from each other, and the angle is negative 90 degrees, so it's directly below. So that's what you want to do. Okay, so now you still want 4, then there's more math. So a lot of times when I'm doing this, I have a calculator because I don't want to risk making a mathematical error on this. So now position is going to be 7.7, and then right below it, you continue here, 7.7, and then 6.5 or 0.65. Subtract it, so this one should be negative 7.05. This part should be 4. Here. And then here, 4, and then 6.4. And so notice that everything is, and doing this is a lot better than trying to drag and place it, because dragging and placing it means that, like, if you want something to be 0.01 millimeters further to the right, it's a lot easier just to plug in the number and then just let it calculate rather than trying to just like fine motor skill move it to the right. So I like using this method a lot more than trying to drag everything and make sure everything's even. And also doing this, oh, I did not. Doing it this way also ensures that all the numbers are correct as well, and you don't have to worry about something being off at all. So this is, so the process can get a little time consuming because it does involve a lot of precision, and you don't want to make any mistakes in doing this because you would have, if you do end up making a mistake with this, and it's definitely not the end of the world, it's completely okay if it happens. But if a mistake does happen, then we would have to reorder the board altogether because we would have to modify the boards or do something to it so that way we can make the footprint fit. Does anyone have any questions so far? Yeah, it is a bit tedious, and it's definitely not, like, for me, you've probably heard me use this analogy before, but I really like PCB design because I kind of see it as, it feels a lot like circuit art, and This part is less of the art part, more of the, you have to make sure that everything is completely perfect in order to make this work out. So this part is definitely not the most enjoyable, but it is definitely still important. Okay, so now we know that this side also has to be 0.65 millimeters away from each other. But since we're on the process of editing its position, we also want to make sure that the center of this is a certain distance, a proper distance away from the center of the pad on the other side. So we go back to the data sheet and notice that they don't actually give us that size. They give us A, which is to the ends, and B, which is to the middle. So we're gonna have to do more math. So this time it's just gonna be A minus B, and that gives us the length of, or it's not gonna, so it's gonna be B plus the length of one of the pads, because we'll have to add half a pad back here and half a pad back here. So the size of the pad is 1.43 millimeters. And we calculated that earlier. We're doing A minus B divided by 2. And then we want to add 1.43 back to 6.16. And you get 7.59. So we want this to be 7.59 millimeters away from this. So to do that, you could go here. You want now the X position. You want to manipulate the X position, and you want to keep the same Y position. So you want to keep the negative 7.25. Now you want to do negative 4, and then you want to add it to the 7.59 that we just calculated right now. So we want pad 20 to be at position 3.59 for X and negative 7.25. So that it's going to overlap. It might overlap with 9. So I'm going to move these to the side here, and then here we're going to edit it. We want this one to be 7.25, so that way it's aligned on the same y-axis. But the X, we want it to be 3.59. And so now notice that those two are aligned. You want to double check it with the inspection tool. You go here, find the center of it, go here, and then, oh, this one doesn't go to 3, it doesn't go to 0.9. So in that case, you would have to make the grid size even smaller to include that. The thing you want to be careful about making the grid size smaller is you do want to make sure that you actually are inspecting it from the center, because it is very, the distance away from it is very, it's very, I guess, sensitive to movement. So you do want to make sure that it's actually in the center of the pad, or else it will give you the false impression that it is either off by some or not off. But if you do the math correctly, then it should be fine. Okay, so this one, now the X value for this one is going to be the same. Well, now you could choose to look at the Y value here. X value is still going to be 3.59. So you edit it. And notice that the more you add to it, the more you lay out, that it becomes easier to lay out the rest of it, because now you already did a lot of the calculations before. So you don't have to redo the same calculations that you already did. So you just keep laying things out here. So then you keep doing this until you have all the pads exactly where you want them to be. It just can take up more time than you want sometimes, but the good thing about making it is that you never have to make it again once you make it. So if you have to remake it or someone else needs it, it's already made. So that's the good thing about making it is that you don't have to make it again, which is nice because it would be very time consuming to have to make it again each time you want to use it. So from here, y. And then one thing that I do suggest doing whenever, if you ever have to make a footprint on your own, is at the very end to just double check everything and to make sure everything's correct, because you don't want to run the risk of accidentally overlooking something, which is definitely, it's definitely possible to happen, and that's completely okay. It's a very detailed process that can take time, and you may even have to step away from it for a little bit and then check it again. And then if you want at any time, and if you want someone else to check over it, I'm more than happy to check over it for you and to make sure that everything is what you would like, and to make sure that everything is actually where we want it to be. Okay, so now, okay, so that's the most important part, is just making sure that the connections to the component that you're making are actually exactly where you want the connection to be. So this is the most important part, is just doing the part that we spent a lot of time working on right now. Before I move on to the next one, it's good to regularly check as well. So let's just check A. A should be 9.02. So I have to scroll in to make sure that it is actually okay. Okay, and it's 9.02. You may have to also make custom. You could also create your own custom user grid. Here, I'm just looking at if it doesn't fall directly there, then I just like notice here it doesn't actually line up there. You could just kind of eyeball it and see that here it's like slightly away from it. So this one should go over by a little bit. Do that. So this one, I think, is 6.16. So notice B is 61.6. C should be 0.46. So you go here, and that should be 0.46. And then D should be 0.65, which we checked D before, but it's good to check it again. There's 0.65, and then E is 6.31. So we want to make sure this top part here, all the way to the bottom, is 6.31. And so now you have all the pads exactly where they need to be. So now the next part is you need to add some stuff to this, I guess, IC, or to this footprint, to make it easier for the user to also understand where everything is. So one thing that a lot of people do is we need a pin 1 indicator to indicate, because if you look here, technically this side is going to look exactly the same as this side. So we want to make sure that we're connecting pin 20 to where pin 20 is, not where pin 10 is. So the way you could do that is you could do a pin 1 indicator. There's multiple ways to indicate where pin 1 is. If you're curious about the different pin 1 indicators, pin 1 indicator, so on an IC like this, a lot of times this dot here will represent where pin 1 is supposed to be. If you look here, they changed the actual connection there. Sometimes you might get like, so here they changed it. Here, if you look here, they might have a dot there, or they may have like an asterisk next to it. So there are multiple ways that pin 1 is indicated. You could choose the way that you want to do, but it's good. You want to make sure that you actually do have pin 1 indicated somehow, because it's important to make sure to indicate it so that way when we're soldering it, that we soldered it correctly, or else the connections are not going to be right. Okay, so what you want to do is use a silkscreen layer to do that. And the silkscreen layer, remember from the earlier tutorial, actually does get printed on the PCB, but the courtyard and fabrication layer do not. So I'm going to describe what the courtyard and fabrication layer actually mean. So the courtyard layer, it's the keep out area for other parts to follow during assembly. So the courtyard area is important because when you're using the design rules check, so the little ladybug when you're designing your PCB, I don't know if you guys remember or not, but the error that came up was that the courtyards overlap. So when you're laying out the courtyard, you're saying that no component except this component should exist in this space. In difference, the fabrication layer is more like a technical documentation for manufacturing and maintenance. So a lot of times people use the fabrication layer to indicate like around the size of the IC or how big it will be or stuff like that. So that way we could do that. But the courtyard and fabrication layer do not get printed onto the PCB. They're only for our use whenever we're trying to design it. And so that way we can make sure that that's properly designed. So let's lay out the fabrication layer first here. So we could do here, in order to get the dimensions of it, we're going to have to go back to the data sheet. So we've gone to the data sheet a lot, but the data sheet is there to kind of be your best friend and help you a lot because it tells you everything that you want to know. So right now we want to know the size of this little rectangle here, and notice that this pin 1 indicator is this little dot here. This dot here indicates that this pin right here is pin 1. And so D is minimum or maximum. I like to go with the max or nominal like size, just because you want to make sure that even its maximum thing could fit, but you also want to make sure that its minimum could fit as well. For now, we'll just stick with the nominal. But a lot of times it's a judgment call that you have to make to see, like in this case, if it's too big, we want to make sure it's able to still fit, or if it's too small. But usually, generally, the error is not too big. Here, it's 0.3 millimeters. And notice that somewhere here, it will tell you what the units are because they did not actually specify the units here. Okay, so D here is going to be 7.2. So we want it to be 7.2. So when you're laying out this line, you could zoom in more and then lay it. You can also change the thickness of it. Like I think this is pretty thick. So you could edit it once you lay it down. Okay, so here you have that. You can edit it. You can change the start point and end point. So this is, and also the line thickness. So I'm going to change it to 0.1 millimeter. Notice it's got a little thinner. Now it's more math again. So you know D is going to be 7.2 millimeters, and you know that the length from top to bottom here is E here, which is 6.31. So if you do 7.2 minus 6.31, and then divided by 2 again, so that way you get the distance from the top, from this pin to the top and this pin to the bottom, and that should be 0.445 millimeters. You go back to the footprint editor, you go here, see, and the important thing here you also remember is it's 0.445 millimeters away from the top of the of this pad. So you have to add back half of its width. So its width is 0.46, so you want to add 0.23 back to it. So you want this line to start 0.65 millimeters on top of it. So you go here, you position negative 7.25. Remember that it becomes more negative as you go to the top, so you add back to it. So you want this to start at 7.9, or you want to keep its x value here. You want this to start at negative 7.925, and then remember that the length, I believe, is 7.2, so you could add 7.2 back to it. So then it should end at negative 0.725. And so now notice that this is the length of the IC is going to be. You could go ahead and copy this. So the weird thing about copying it is once you select, and this goes for when you're actually designing the PCB as well, you could click on it and you press C, but you need to, once you press Control C, you actually have to select exactly what you want to copy. The Control V again, and then okay. So now we want to make sure that this is aligned to this. Okay. So here, okay. So this one should start also at negative 7.95, and this one should go to 7.25. And so now they're aligned again. And now you could also look at the distance. You're looking at E1, that's 5.3. So this distance, if you take 3.28 and then add 5.2 or 5.3 back to it, you should get 2.02. So that's where you want this to be. Actually, I don't think that's right. Okay, as you can see, yeah, I don't think that's right. But in this case, you might want to just leave it like this so that way it's an edge. Not usually things should fit together fairly well. In this case, it doesn't look like it actually fits as well as you'd want to. But another thing you also want to note is that this isn't going to match the recommended PCB footprint because they did try to make some room for error on the recommended PCB footprint, so that way we know exactly how, I guess, far so that way there's a little leeway, so that way if the PC, like the component can move a little bit and it still be connected to it. So now you want to finish closing off this, so you could use this line, connect it. Okay, I'm gonna edit it to make it 1 millimeter. I'm gonna edit this one here. Also be 1 millimeter. Okay, one. Okay, so now you have the fabrication layer. You do want to probably move this a little bit lower so that way it's there. So now you kind of have the general gist for the user to see that it's going to be around this size. It might actually be a little smaller, but I will leave it like this for now. And then I like to do the courtyards last. So now the reason why I like to do the fabrication layer before the silkscreen layer, so that way I could put the silkscreen layer just surrounding the the fabrication layer. So here, if you go to here, and then you're laying it out, you can lay it out. Let's do. Okay. And there's no hard fast rule for how or like what to do the silk screen over. But generally, it's just nice to kind of do something where it kind of covers the outline of it, but doesn't have to go into extreme detail, or it has to like cover everything. So here, I'll probably just do like the top and bottom, and then like the pin one indicator. Here, like the pin one indicator that I'm thinking about doing is just carrying this line over here. So now we know that this should be pin one. And so now I'm going to finish doing this here. Okay, so now you have that pin one indicator. If you want to be certain that people don't accidentally mix this one as pin one, you can make a little dot here. You can move it there, and then you can fill it in. There actually is no fill in thing here, so you just have to use a bunch of lines to cover it. Okay, so now you have this, and now this is a footprint that you're able to use. For our last step, you want to add something to the courtyard layer, and so just generally you could just make like a rectangle that kind of surrounds it. I don't know if there's actually if there's a better way of like estimating the courtyard, but usually I just like just doing a rectangle around it, and yeah. I'm gonna make the grid size a little bigger because I would say grid sizes, having it grid size bigger just makes things easier to work with, because now it's a lot easier to make a straight line because you're only allowed to move 0.1 millimeters as opposed to 0.01 millimeters. So now you have the courtyard layer, and that's I'll probably go ahead and center this. To the best of my ability. And then now you have your footprint for it. And make sure you save it as well. And we could save it. Oh, and here we could create a new folder for it. We say new library. We could just say workshop, and it's a .pretty file. We save it. Keep it in global, and then we could edit, or we could now save it to the workshop.pretty library here. Okay, so now we have that. So let's go back to the symbol editor so that way we can add that footprint to the previous symbol that we just made. So we go here, we can double click that, go to edit symbol properties. Now we can find the footprint that we just made. Go to workshop, and the AS8510. When you see it, this is the exact same one that we just made, and then you press OK. So we could save this new symbol here, and now when you go back to the, so for now I'm just going to, this should actually be connected to something eventually, but just for the sake of time, we're not going to worry about that, and we're going to see what it looks like on the PCB. Yeah. So I'm gonna do this, finish annotating it. Oh, okay. So another thing you want to do is when you, let's say you edited this symbol, it's the edits to it, if you've already laid it down, haven't been added to it yet. So you, I think the best way is just to re-add the symbol here. You can save it, annotate, update PCB. And so now here's um, the IC that we just made and the footprint we just made that we can use now. So is there any questions over what of anything that I just went over? I know this was a lot to take in today, so um, I have a video of this that I will upload onto the Google Drive as well that you can refer to at any time. And I'm gonna stop the recording here now, but I'm gonna continue talking for a little bit longer just to describe some of the projects that you can start on if you don't have a project already. So